So now guys, in this video, we'll be explaining now different gas laws. And here we're going to start now with the Boyle's law. And so with the Boyle's law now establishes, guys, the relationship between the pressure and volume. And the way now the Boyle now discovered his law is that he used this J-shaped tubes, and with the J-shaped tubes, guys, he was able to construct the manometer that are covered in video number 1. So what he did is that he used the glass tube, and he used now mercury as the substance that will, the height of mercury will be now measuring the pressure of the gas that, let's say, has been captured here. And let's say we started with 100 milliliters of this gas. The volume is 100 ml. And so he started with the mercury, and the mercury level was just equal, whatever the level here mercury was equal to mercury there. So this is my mercury here, Ag. And guys, remember this now, right now, open to the atmospheric pressure. So now the gas molecules and atoms now exerting pressure on this side of mercury here, and the gas that is captured here is also exerting pressure on this side of mercury, and both levels right now are equal. So the P of the gas in this manometer is equal to the P atmospheric, which is a 760, let's say, millimeters of mercury here. Now, so the next thing he did is that, again, he just added to this J-shaped tube, he just added 760 millimeters of mercury. So he doubled the pressure here. He doubled the pressure. And what he observed now, the volume now went down to 50 ml. The volume of the gas went down to 50 ml. He doubled now the pressure by adding 760 millimeters of mercury here. So this is 760 millimeters. So in other words, he now doubled the pressure again. And so now the pressure for this gas is this. Now the pressure for this gas, P gas, is equal to now P atmospheric plus 760. That will be just the double. In other words, 760 multiplied by 2, or 760 plus 760, and that will come out to 1520 here. So there will be P of the gas now is equal to, let me just correct this. Let me just correct this real quick here. So that will be the P of the H of the mercury plus P atmospheric, and that will give us 760 now of added mercury that we just added P height, and plus millimeters of mercury plus 760 that was originally, the tube was open, that was now coming from the atmosphere or exerted by the atmosphere. There will be 1,520 millimeters of mercury. Now, the next thing he did is that now he used, again, the same J tube. And again, sorry for my guy's drawing, not the greatest one, but I will do my best again. So there it is. So let's say, so now what he noticed after he added another 760 millimeters of mercury now, let's say this is here. Now the height of mercury here, let me just draw all of this mercury here. And should be this shape here of the meniscus. So now this whole thing now is 1520 millimeters of mercury now, the column of the mercury. But don't forget, there is also P atmospheric. It's open, guys, to the atmosphere. So it's another 760. So what he tripled the pressure, guys. Now the gas that he measured was 33 ml. And so with this experiment, now let me just put down now the pressure. There's a gas in here now captured. So the P of the gas is equal to now the P due to the height plus the P due to the atmospheric pressure. So that will be now 1520 millimeters of mercury plus atmospheric 760 millimeters of mercury. That would be now plus 760 came out to 2280 millimeters of mercury. So they triple the original pressure, and the gas now reduced by 1/3. So what he was able to establish is the inverse relationship between the pressure and the volume. So he said that now from his experiment, P times V is equal to some constant, or P is equal to constant over V. And from this experiment, guys, it's obvious that every time the pressure was increased, the volume was decreased. So that was valid now relationship mathematical between pressure and the volume. And so graphically, now we can express this relationship. I'm going to put it here in the corner. I don't really need much of the space here. So if you got volume here in liters, now is a function of pressure here, millimeters of mercury. So when he plot these values here, he got this curve, which is not straight. So with this curve that is not straight, it's very hard to interpolate the data for the pressures. For example, if you now want to figure it out, what was the volume now? Somewhere between 760, let's say, and 1520. With the curve like this, you wouldn't be able to do it. But if you modify this graph slightly, and you're going to plot now the volume and milliliter versus 1 over pressure, 1 over the pressure in millimeters mercury, you now will, when you plot these data points, you will now get a straight line. And so now doing now 1 over the pressure now versus volume is a function of 1 over the pressure, you will get now the straight line, and you may actually now get the volume of let's say different pressures. You can interpolate now the volume at different pressures without even doing the experiment, because now you got the direct relationship between the volume over the pressure. And now this is no longer a curve that has no linear relationship. Now this has a linear relationship, and therefore now you guys be able to interpolate the data here. So I'll see you guys in the next video. I'm going to now start solving problems on Boyle's law. And so I'll see you guys now in video number 4.